So in this video, I would like to take the work that we have done with Laplace transforms and apply it to a couple of real-world problems. In particular, we're going to apply the theorem from yesterday, which is how to take the Laplace transform of a piecewise function. So the first problem that we're going to do is the one that is concerned with a beam which is being bent or deflected underneath a load. So if you have some horizontal beam, a load which is measured by the function w of x is imposed by the beam on the beam at position x, then the beam undergoes some deflection from its normal horizontal position. Maybe the actual beam ends up somewhere down here. The vertical difference between the beam's normal location and its location under this load is called the deflection. And the deflection satisfies a fourth order ODE, two constants called E and I, which depend on a lot of different factors, in particular factors concerned with the material of the beam. The fourth derivative of y is equal to the load at any given point x. Now let's use that differential equation in the following exercise. We have a beam which is 10 units long, which is embedded at both ends. Now when the beam is embedded at both ends, as in the given photo, that has some implications. It has the implication that at both ends, at both x equals 0 on the left end of the beam, and x equals 10 on the right end of the beam, the deflection, and in fact the rate of change of deflection at those two positions, all of that is 0. So y of 0, y prime of 0, y of 10, and y prime of 10, all of those are equal to 0 for a beam of length 10 which is embedded at both ends. So now suppose that there's only a load on the left half of the beam. On the right half of the beam, the load is 0, but on the left half of the beam, there is a load which satisfies the equation 1 minus 0.1 times x, where x, again, is the horizontal position along the beam. Let's see if we can figure out the deflection of the beam under these circumstances. So I'm going to start with our differential equation, e times I times y to the fourth power is equal to our load function. So I'm going to rewrite the load function using unit step so that I'll be able to transform it. So I'm going to start with the function 1 minus 0.01 times x multiplied by the unit step function, which activates when x is equal to 0. And then I'm going to add the unit step function, which activates at x equals 5. And I'm going to use that switch to turn off the function 1 minus 0.01x and to turn on the function 0. Now that I've done this, I'm in a position to apply the Laplace transform. And I'm just going to denote the Laplace transform of y by capital F. I prefer F to capital Y just because I think it's easier to distinguish capital F and lowercase y than it is to distinguish capital Y and lowercase y. Now when I do that, EI is just a constant. So now we have the Laplace transform of y to the fourth derivative. And on the right hand side, we have the Laplace transform of 1 minus 0.1 times x multiplied by the unit step. And then we have the Laplace transform of the same function being subtracted multiplied by a different unit step. Now on the left side, we can write down an expression for the Laplace transform of the fourth derivative. I'll start by taking 4 powers of s multiplied by capital F, then 3 powers of s multiplied by y of 0, then 2 powers multiplied by y prime, then 1 power by y double prime, and then no powers by y triple prime. Meanwhile, on the right-hand side, the Laplace transform of 1 minus 0.1x times the unit step which activates at x equals 0 is the same thing as just the Laplace transform of 1 minus 0.01 times x. But to find the Laplace transform of the second term, where we're multiplying by x minus 5, the first thing that I need to do is shift this function in the opposite direction by 5 units. So I need to replace all the x's with x plus 5's. That gives me the Laplace transform of 1 minus 0.01 times x plus 5, and then I'll multiply by the corresponding exponential e to the minus 5s. Now in my initial conditions, because the beam was embedded, I know that y of 0 is equal to 0, and y prime of 0 is also equal to 0. But what's interesting about this problem is that, as of this moment, the values of y double prime and y triple prime at 0 are actually unknown. So for short, I'm just going to call C1 the value of y double prime of 0, and C2 the value of y triple prime of 0. With that, the left side becomes e times I, s to the 4th power times s, minus s times C1 minus C2. And on the right-hand side, the Laplace transform of 1 is equal to 1 over s, and the Laplace transform of x, who is taking the role of t in this problem, is given by 0.1 divided by s squared. In the back, the e to the negative 5s is being multiplied by the Laplace transform of this shifted function. Now I can simplify that shifted function as 0.5 minus 0.1x. The transform of that expression is given by 0.5 divided by s minus 0.1 divided by s squared. So now I have a fully transformed equation, and I'm going to try to solve this for f. So the first thing that I'm going to do is I'm going to divide out EI (1 over EI) times the quantity 1 over s minus 0.1 over s squared minus e to the negative 5s, 0.5s minus 0.1 over s squared. And I'm going to move these two terms that don't contain any f's to the other side. And then I'm going to divide through by s to the 4th power. So if I want my solution, if I want the function which gives me the deflection at the location x, all I have to do is find the inverse Laplace transform of this expression. For example, if I wanted to find the inverse transform of C1 over S cubed, I can do that separately, and that will be equal to C1 over 2 times t squared using our table. The second term, likewise, is equal to C2 over 6 t to the 3rd power. Then I have our constant multiple of plus 1 over e times I, inverse of 1 over s to the 5th power, which is equivalent to 1 over 24 t to the 4th power. And then our constant multiple of 0.1 over ei. And then the inverse of s to the 6th power, which is 1 over 120 t to the 5th power. Really, the two terms that are going to cause us the most difficulty are the terms which are being multiplied by this exponential. Our theorem says that if we want to find the inverse Laplace transform of an exponential multiplied by another function, start by taking the inverse Laplace transform of that other function. Then in the result, replace the t with t minus 5, corresponding to the negative 5 in the exponential, and multiply the result by u of t minus 5. So if I take the inverse Laplace transform of this little bit in green, then I get 0.5 divided by 24 t to the 4th power, minus 0.1 divided by 120 t to the 5th power. And I'll need to replace those t's with t minus 5's and multiply by the unit step, shifted 5 units to the right. So that gives me 0.5 divided by 24, t minus 5 to the 4th power, minus 0.1 divided by 120, t minus 5 to the 5th power, multiplied by the unit step, which also has t minus 5 in it. So finally, putting together our result in blue with what we just calculated for the inverse Laplace transform of this quantity in the parentheses, we get a formula for y of x, and that's going to be a lot of writing, so I think I'm just going to copy paste it. Alright, so here's our formula for the deflection of a beam, and while I was copy pasting this, I caught the fact that I had been using t by accident instead of the correct input variable for this particular problem, which is x. So all I've done is I've just gone in and replaced all the t's with x's to be more consistent. Now there's one unresolved issue here though, which is that we still don't know the values of C1 and C2. The values of C1 and C2 are still unknown. And this is the moment where we're going to try and use the fact that y of 10 and y prime of 10 were both equal to 0. Hopefully these two pieces of data will be enough for us to determine the values of the two coefficients that are currently unknown in our equation. Now, as I'm going to investigate what's happening to this function at this location where x is equal to 10, I'm going to note that when x is equal to 10, and everywhere in the vicinity of x equals 10, the unit step function in the expression has a positive number plugged into it, and therefore is going to output 1. And so for all the calculations that we are about to do, we can treat this unit step factor in the back as if it were just 1. So, as a result of treating the unit step function as just 1, for the purposes of these calculations specifically, we get to reduce our function to something ever so slightly simpler. So having noted that, finding y of 10 and finding y prime of 10 is going to be tedious, but it's not going to be complicated. All that we're going to need to do is plug x equals 10 into this expression, then find the derivative of this expression and plug 10 into the derivative. So that's straightforward enough that I'm not going to bore you with the details. I'm going to use technology to do that off screen, and I will come back to you.
6.5 hours later.
Well, folks, it's been about 7 years, but I have finished calculating the value of y of 10 and the value of y prime evaluated at 10. And as you can see, we get a system of two equations here containing the two unknowns c1 and c2. So this is a system of equations which can be solved for c1 and c2 using any of the traditional techniques, for example, elimination or substitution. Once again, that's just a bit of tedium, so I'm going to go ahead and solve this system probably using method of elimination, and I will be back in just a second.
2,000 years later.
Well, hopefully that's correct. So after some work, we have found that C2 is 32 divided by 3 times EI, and C1 is equal to negative 305 divided by 18 EI. So to find the deflection, I would plug those numbers back into the formula for y of x that we found above. So this would be the function that gives us our deflection. So let's consider an example where we have a 32-pound weight stretching a spring by 2 feet. Now right away, we can find the mass of the object by taking its weight of 32 and dividing it by the acceleration of gravity in imperial units. So the mass in these units would just be equal to the number 1. We can also find the spring constant from this data. Our weight force of 32 is stretching the spring by 2 feet, and therefore in these units, the value of K would be equal to 16. Now we're told to ignore any damping forces, but we do have driving motion given by the function f of t. F of t equals 20t, but only acting on the system between times t equals 0 and time t equals 5. After that time, the driving force is removed and becomes 0. So our equation for the spring, y double prime plus the spring constant divided by the mass times y plus the driving force divided by the mass. Since the mass is just 1, this is equivalent to y double prime plus ky is equal to f of t. We found that our k was equal to 16, and our driving force is equal to 20t from time 0 to time 5. But after time 5, the driving force is removed and is reduced to 0. Now we're also told that the mass attached to the spring is attached from rest and from the equilibrium position. So from equilibrium position means that y of 0 is 0. From rest means that y prime of 0 is 0. Using this data, let's go ahead and find the equation of motion for the object attached to this spring. So I'm going to start by rewriting the forcing function using unit steps. So we start by turning on 20t at time 0, and then at time 5 we turn off 20t and turn 0 on. So we can write this as y double prime plus 16y is equal to 20t times unit step minus 20t times a shifted unit step. So now if I apply the forward direction Laplace transform to both sides, the y double prime becomes, I'm going to call it y capital, just because in this case f of t is being used to represent the forcing function, and I don't want it to get mixed up with the solution to the actual differential equation. and the transform of 16y I'll write as 16 capital Y. The transform of 20t times the unit step, which turns on at time 0, is the same thing as the transform of 20t by itself. But to find the transform of 20t times the shifted unit step function, I need to take the corresponding exponential and then transform the function that I get by taking the t's and shifting the t's in the opposite direction, t to t plus 5. Since y of 0 and y prime of 0 are both nothing, the left-hand side simplifies to s squared times y plus 16 times y. And on the right-hand side, the transform of 20t is 20 divided by s squared. And the transform of 20 times t plus 5 is equal to 20 over s squared plus 100 over s. So the function y, which is equal to the transform of the equation of motion, satisfies 20 divided by s squared plus 16, minus e to the minus 5s, 20 divided by s squared plus 16, and 100 divided by s squared plus 16. Now, in order to stand a chance of applying the inverse Laplace transform to this, you're going to have to do a partial fraction decomposition. Once again, I'm going to do that off screen using technology, just so that I don't bore you with those calculations which we have done several times by now.
One eternity later.
And the expression in green is the one that we need to invert in order to get our solution, the equation of motion, y of t. So if I invert 1 over s squared, then that's equivalent to t. If I invert the 4 over s squared plus 16, then that's equivalent to sine of 4 times t. Now, in the parentheses, it's a little bit more complicated because we're trying to invert something which has been multiplied by an exponential. So I'm going to find the inverse transform of the stuff that's being multiplied by the exponential. But in the result, I'm going to replace all of the t's with t minus 5's from the minus 5 in the exponential. And then I'm going to multiply by the unit step, which is also shifted 5 units to the right. So after executing that step, we get 5 over 4t minus 5 over 16 sine of 4t. We get 5 over 4, not t, but t minus 5. We get negative 5 over 16, not sine of 4t, but sine of 4 times t minus 5. 25 over 4, not times t, but times t minus 5. And not cosine of 4t, but cosine of 4 times t minus 5. All of that multiplied by the unit step function. This would be our equation of motion for the object attached to this spring in the case where we had applied a driving force for a little while, but then we removed the force after time t equals 3. The solution to that equation is given by this monstrosity here in green, blue, and yellow, which doesn't even quite fit on screen. That concludes today's material. We applied the Laplace transform to a few problems of a more authentic nature, namely to the deflection of a beam and to a spring mass system where the driving force was represented by a piecewise function.